We'll now go to our second presentation of the day. We have two speakers for this presentation, Jeremy Chang and Linus Lim, who are both with Holmes, both technical directors at Holmes. So Jeremy is with Holmes New Zealand and Linus with Holmes Australia. So Linus, Jeremy, the floor is yours.
Thank you, Thomas. So I'll start talking first. It's Jeremy Chang from Holmes New Zealand. What we are going to talk about today is utilization of SAFIR for structured file assessment in forensic and design application. What I'm going to talk about is the design application, and then pass to Linus to talk about forensic. So performance-based structured file design is one of the main service our company provides. And let's not talk about performance-based, but I mean just simple structure file engineering design that can be done by all the structure engineers. That's not something super special. I think most people are aware that you have the design standard that you can follow for simple calculation, and all the structure design do need to consider about the fire effect. But the finite element analysis is something that we want, it's more specialized, and our preference is to be engaged with the design team early, and then we can push for the finite element analysis. And the problem with using finite element analysis in design is we need to make sure the results can be reproduced. And that's not only about getting the input data and run the simulation again. It is using the same parameters in the design, and then someone else can reproduce the results, which means the computer package does need to be robustly reviewed. Need to be peer reviewed, and enough evidence to back out the computer package. And also the package cannot be too easy to be manipulated. There are quite a few programs out there that people can play with the relationship, like the thermal relationship, mechanical relationship in the background, and then those tend to be quite difficult to be peer reviewed. And if things are being difficult to be peer reviewed, it will be difficult to use in design to get approval, basically. And one other reason why we prefer to use SAFIR over other programs is it is reasonably easy to use in terms of finite element analysis. So I think while most people are here would agree that SAFIR is the easier program to use, and I don't really have to sell that too much. What I'm going to present here is one of the design examples we have in New Zealand. It's the Dunedin Hospital, which is down south. There are two buildings. One is inpatient and outpatient. Inpatient building, we are still doing the analysis at the moment. The outpatient building has been completed in terms of the design and also the council approval. The building will be suitable to use after major disasters. In New Zealand, what that means is major earthquake, and for that, this hospital is protected by sprinkler system with dual water supplies. Under the New Zealand Building Code, even if you have dual water supply with basically all the passive fire protection systems thrown in, you still have to consider what if the sprinkler system fail. So that's what we came in, and the structure design is with steel moment frame acting completely with 170 millimeter concrete floor. The composite concrete floor is called tray deck, which has the profile next to the text. So it has a relatively flat bottom, and then that will touch the top flange quite nicely, so we won't really have a void between the top flange and the concrete. Each bay is 8.4 meter by 8.4 meter, so it's rectangular. For structure fire engineering design, we have to follow the same process as fire engineering brief, like the normal fire engineering design, just to explain the design file we choose. This way, we can make sure that, later, because running a simulation does take time, and we want to make sure everyone is agreed that the the chosen design fire are the ones that people believe that's representative. And for hospitals, we do need to think about the decay phase. So rather than just using the ISO fire, we look into the parametric fire. The problem with parametric fire is, for example, the scenario 1, which is the operation room. It doesn't have a lot of ventilation area. Basically, it has almost no ventilation area. And the parametric fire in the decay phase is going to be super long. And that's actually quite unrealistic. And the decay phase, well, the structural behavior is quite different from the heating phase. And that long decay phase is causing problem. But that is something we have to analyze, and then we have to discuss further. The acceptance criteria, well, there are no hard restriction on the flow deflection. This took a lot of communication between us and the other stakeholders, because many people don't really appreciate that the structural fire analysis, or when the floor is going to deform, that's very late into the fire, and this is not really relevant to the life safety of people above the heated floor. So the deformation shape, well, I mean, we don't want the floor to collapse, but how the floor is going to deform, that is nothing to do with how people can get out from that floor. And that's why we don't really, well, put a hard restriction on the floor deflection, like whether it's L over 30 or L over 20. What we do need to worry about is there will be no runway failure. So we don't want the floor to collapse. We don't want local or global collapse. And then the mechanical strength of concrete reinforcement doesn't exceed 10%. That is something we put in to just make sure the floor, well, there is some limitation on the simulation, so it just doesn't run indefinitely. This is the model we simulated, and then with different reinforcing bars that come up with different sections, and then we pick a corner of the building to simulate. Did this thermal analysis for the primary beams, and then also we did the thermal analysis for the unprotected secondary beams, and also the thermal analysis of the shell element simulating the slab. And the simulation results was, well, it kind of as predicted. The maximum deflection happens when the temperature is high, and then start to come back a bit later. Most of the secondary beams are allowed to be unprotected. That's what the client wants. Beams within 700 mil from the evacuation zone's boundaries are protected. That is to appease the other stakeholders. We actually don't really need that. The primary beams and columns are protected. And for either way, like, well, all the performance structure design, we do ask people to pay special attention for the connection, just so, well, the shear force can be passed into the concrete infill of the columns. And that's that's the example I'm giving for the design stage, and I'm passing to Linus to talk about the more interesting side about forensic.
Hi everyone, you can hear me?
Yes, Linus.
Thank you. Hang on. Why is it not sharing? There's the share again. Sorry. I'm not used to sharing screen. Why is it not sharing? Can you see my presentation?
You are sharing. You are sharing.
Yes.
Okay, can you see my presentation? Cool, good. So today I'm going to talk about the post-fire investigation and analysis of the New Zealand International Convention Centre fire. Some of you might have heard of this before, so apologies if you feel like it's a repeat. But anyway, I'm just going to talk about it, try to compress it in 15 minutes. So firstly, the building I'm going to talk about is a building that was approaching completion in New Zealand, in Auckland. This is roughly what it looks like. It's several stories over here, and each floor is about 8,000 square meters per floor. And inside the building is going to be used for a large exhibition hall. And then here you have a theater which has got a sitting height of about 13 meters. And the theater can accommodate up to 2,800 people. And like I said, it was nearing completion, but a fire broke out in October 2019. So this is quite a few years now. And what you can see over here is a time lapse. Conveniently, there was a video webcam camera located on a crane, or actually next door building, which captured it. So I'll try to run this. As you can see, it started from one side and it spread across the roof, and it burned for nearly 4 days. By the time it was fully extinguished, but the main part of the fire was about 2 days. So it went from the upper roof, and then it spread to the lower roof, and then people thought it'd gone away. But then for some reason, it starts here again on the other side of the roof. So the firefighters had a tough time putting out the fire because there were concerns of trying to approach it from the underside, so they had to fight it from the outside, from the street level. So anyway, that's the video. Oops. So a bit about the structural system to which we did this investigation for. It's a fairly complex steel frame structure. Is designed to resist not only just gravity loads, but also earthquake loading. Coincidentally, most of the steel frame structure, including the long span trusses, were protected with intumescent paint to a 90-minute fire rating. There's two parts. The structure has got the upper roof and also the lower roof. The upper roof here, you got blue here. Blue is the secondary trusses, which span about 40 meters between the red ones. The red ones are the primary trusses, and the primary trusses, you got columns over here. You can see my mouse, right? The primary truss is about 36 meters spanning this way, but you got 40 meters. The main span is about 40 meters this way in the blue. And on the lower roof, you have trusses over here, which span about 27 meters, up to 27 meters. What happened during the fire was that in the composition of the roof, the roofing membrane consists of this layer which is combustible on plywood, and then you have thermal insulation, and there's a void, and there was acoustic panels, but someone accidentally left the heating torch when they were trying to build up the roof membrane, and then the heating torch set the plywood on fire, and then thermal insulation caught fire, and then air passes through the void, and then it just went through the whole roof layer. So also there was prevailing winds that caused the fire to spread everywhere. So after the fire, these are some photos of what the structure looks like. So you can see this is the primary truss. Sorry, this is a secondary truss. You can see the white over here. The white is the activated intumescent paint. There's debris falling on the ground over here. And then also, again, another photo, you can see activated intumescent paint throughout parts of the structure. That's the upper roof. In the lower roof, there's not generally, by and large, there wasn't a lot of damage to the structure, not a lot of significant damage to the primary structure. This is only one of the few examples where there was significant damage. Most of the structure, there was no deformation to the structure. The secondary structure, the purlins were damaged, that's true, but the big trusses were fine, mostly. So we were asked to look at, to undertake an investigation to answer a few questions. Has the structure suffered any long-term loss of strength? Were there any high fire-induced residual stresses, and could these stresses in future, if they kept the structure, could they overload the structure under gravity loading or seismic loading? So in terms of our investigation, we had to work out where was the fire, how long was the fire, and the intensity of the fire, how much of the structure was exposed to the fire. And whilst there was some deflections, it wasn't clear at the time what caused them. And also the challenge was any thermally induced residual stresses due to the fire were not that easily visible. So to understand the extent of heating to the structure, conveniently, like I said, the whole roof structure was painted with intumescent paint. So we could observe that there were different levels of activation of intumescent paint. So we worked together with the intumescent paint supplier to sort of work out what the different appearances of the paint look like. For instance, over here, this is between 100 to 20 to 100 degrees. And gradually, as it gets hotter and hotter, you can see different levels of bubbling in the intumescent paint, and then activation, and then even hotter activation. And then the paint supplier was able to advise us, okay, these are the different temperature ranges. And we could assign the temperature color coding system to the different temperature ranges, right? And then we did a whole bunch of inspections throughout the building to work out, where the heating was. Purple here is a low heating, and then you have different levels of heating, orange and so on, which have areas of much higher heating. So we did this for the whole roof structure. Took quite a bit of time, obviously. And then the other thing is also to try to work out when the fire was and where the fire was. So we mapped the heating progression of the structure of the fire across the structure using the webcam video. So fundamentally, the fire started to move from this way, in the blue to the green, purple, and so on, from this way to the northwest to the northeast, and then down south. So each of these regions from the CCTV footage, we could see you could have time heating curves, very simple time heating curves, approximated like this for each of the zones here, 1, 2, 3, 4, 5, 6, 7. And then we were able to define what the heating was. One of the other things also that we thought we should model was the presence of the intumescent paint, which compared to vermiculite fire spray looks a bit like this. So intumescent paint has got this bilinear curve. We did a bit of simple literature survey, and we worked out that the temperature is going to active with the intumescent paint is going to activate a bit like this, right? It's to define limiting temperature. If someone protects a bit of steel to a certain limiting temperature, you would have a characteristic curve that looks a bit like this. So we tried to model it this way. And the reason why we modeled it this way was we wanted to capture the phenomena in the early heating zone as well, because of the influence of residual strains, particularly when you look at the stress strain curve of steel. At 200, 300, 400 degrees Celsius, you start to get some nonlinear behavior. So when you have heating and cooling and unloading, you would get some residual strains over here. So we want to make sure that we sort of pick some of that up as well. So coming over here, backtracking a bit. So we took all the heat transfer analysis for every single different type of structural element to the different heating curves, temperature time curves, and zones. And we construct a structural model looks a bit like this. And we ran it, to see how the structure responds. And if you look at the deflection at the top of the truss over here, it looks a bit like this orange curve here. So this is the net deflection, this attributed to fire. So we cancel out the gravity deflection. So I'm only showing the net deflections. So the structure deflects upwards. This is vertical displacement as a function of time. It displaces up and then comes back down after cooling. So there's a little bit of net deflection, but very impossible to see with the eye. But fundamentally, the structure is pretty much undeformed, at least over here. In other areas, we were also able to predict the deformations, which were quite consistent with what we saw on site. So one of the things I said early on was that we were trying to predict where the residual forces are. So this is the plot of the axial forces after the fire at the top chords of the roof truss. So blue is compression and yellow is tension. So in theory, most of the top chord should be in compression, but if you look at this one here, it's actually strangely in tension. So if you look at the axial force, at the start of the fire, it is compression, which is correct. And as the fire comes along, it gets hotter and hotter, and the compression forces increase. But as it cools and decays, you find that, whoops, there's actually a difference. So you forming some residual forces in the top chord, to which we found also by disconnecting numerically the braces, we could actually relieve some of the residual forces and bring it back a bit closer to what it should be before the fire. So all that was quite useful. In summary, we found that all this information was very useful for the team in terms of rehabilitation of the structure. And then fundamentally, what they ended up doing was disconnecting most of the structure and repainting the structure, bringing it offsite, repainting it. I'll just show one last slide here, which is they did some proof load testing. What they did was, this is not SAFIR related, but what they did was they set up a rig. You can see these are tension rods here. So they loaded some of these trusses to ultimate limit state loading to check that the structure performs elastically, to which it did. So it gave confidence to the design team that the structure, even the worst heated one, if they replace one or two members, they could the structure still perform pretty elastically and could take the ultimate limit state loading. Yeah, so look, I'm going to conclude my presentation here. Thank you for your time. Let me know if you have any questions.
Thank you very much to both Jeremy and Linus for these presentations on the designs and forensics part. That was really, really interesting. We have a few questions in the chat. So first one is for Jeremy. Can you please elaborate a little bit on the mechanical boundary conditions in your design presentation on the hospital, especially if there is lateral restraints provided by the cold parts when you were looking at the fire scenarios in the different compartments?
Right. So we didn't really model the cold part. We simulated the entire thing being, well, the whole slab being heated up by the design fire, and the boundary condition, is done. We also model it to the half of next base. So basically, the boundary condition is for symmetry. You have to restrict the lateral movement anyway, and that's what we did. So it wasn't really considering the code part providing restriction, but more to just simulate the symmetry.
Very good. Thank you. Linus, a few questions on your part as well. There were a couple of questions on the intumescent coating. So you presented a curve with the temperature, but can you elaborate a little bit on how you treated that in the thermal model, please?
Yeah, sure. We looked at the different thermal conductivities for different temperatures. So at low temperatures up to about 300 degrees Celsius, we use a very low thermal conductivity. And then once, sorry, the other way around, a high thermal conductivity. And then once we got to past 300 degrees Celsius, we use a low thermal conductivity to represent the insulative effect of the expansion of the intumescent paint. So the thickness of the intumescent paint is modeled as a thin layer first. It's a dry film thickness or whatever it is. And then we just adjust the thermal conductivity. We did some literature survey done by other researchers, and they've pretty much done this same approach, to which we just take the same idea and try to do that. Obviously, there are different types of intumescent paint, so we make sure we were sort of within the same sort of tolerance and boundary that was reported. It's not an exact number. It's just a bit of calibration to try to adjust it to bring it to this sort of design limiting temperature. For instance, we have 550 limiting temperature to 90 minutes, so we just adjust these parameters as such.
Very good, thank you. Yes, so in the SAFIR thermal model, the geometry is not changing, right? That thin layer has a fixed geometry, but you're back calibrating thermal properties to get the behavior.
Yeah.
Very good. So another question for you, Linus, from Jean-Marc. How did you disconnect the braces in the model? You mentioned something about that.
I think it was with the relax function, Jean-Marc. I can't remember. This is like 3 or 4 years ago, and it's probably quite a painful memory. But I can assure you it was something that we did using one of the new functions that you introduced at the time to relax the axial degree of freedom, so that there's no restraint from that member. It actually worked out quite well because we tracked the axial forces. Suddenly there's no axial force in there once we relax it.
Yes, right. Great to know you use that function, relaxations for the end of the beam elements. Good. So yeah, we still have a few questions, a few minutes, and there is lots of interest. Another one for you, Linus, about the fire curve that was used for the thermal analysis. So that was complex. You showed the fire traveled. It lasted for a very long time. In the end, how did you go about selecting your fire to apply in the model?
This is for the this thing over here.
Yeah, for the
this
thermal
was
analysis of the members with the intermittent coating, for example.
Yeah, so like I mentioned, for every single member that we able to map, oops, let me just go back here. So for every single member, we were able to observe, we could work out what the likely maximum temperature the steel was exposed to. And then, like for instance, here this would be correlating to about say 300 degrees Celsius, and then after that we would then adjust the temperatures for the temperature time. Oh, let me just share my screen again. It might be easier to explain that. Yeah, might be easier to explain. Here we go. So for instance, over here, this one would have say a maximum of 350 degrees Celsius. So that if we find from our heat map, you know, if you've got a member that's exposed to that temperature, then you adjust the heating so that it would go only up to a maximum of 350 degrees Celsius. And then this one here, it goes this one here, it'll go a bit hotter. It'll be sorry, that would be 400 degrees Celsius. It'll go up only up to a maximum of 400 degrees Celsius. So that's how we define the maximum temperature. And then the time is based on what we observe from the CCTV footage from the top. So in this zone, say in the green zone, it would follow the heating that follows this time here. From what we observe from time 0, it will go up and then flat line. So if it was 400 degrees, that member would be heated to 400 degrees and come down again after we see the fire decay. If you got another member in this zone that's heated to say 600 degrees, you know, it will go up here to 600 degrees and come down again. So every single member in this zone will have its own curve. So there are a lot of curves to be applied to all those members. And again, you know, all the members here could be different. So it was quite tedious.
Very impressive. Thank you. Yeah, I'm assuming that took more than a couple of weeks working on that.
No, it took longer than a couple of weeks.
Excellent. There was the last question, and Jeremy already answered in the chat, but I'm going to read it for everyone. So the question was about the behavior laws, the material laws used in New Zealand, and for the design example, whether you know, they use thermal and mechanical models from the Eurocode or others. But so Jeremy, thanks for answering that. New Zealand standards also use the same material models as the Eurocode. To a large extent, that's the case also in the United States. But by the way, for concrete and steel, it's compatible. So the Eurocode models, which are pre-embedded in SAFIR, were used also in that design example. Very good, thank you. So with that. Oh, sorry. Okay, that's a very just the last question, and I'll ask for a brief answer. But that's a good one. It's interesting. For Linus, do you think there was an effect of rapid cooling from the firefighters on the residual mechanical properties of steel? Maybe even, you know, beyond the modeling of SAFIR. Was that something that was discussed or of concern? Or the effects of water? I know it was very significant in the repair, right?
Yeah, there was certainly a lot of concern about that, but I can assure you that there wasn't that much. The cooling of the steel wasn't that quick, only because the fire brigades just couldn't get to it fast enough, because the reality of it was that a lot of the steel was shielded by the roof itself. You know, there's a layer of the roof, and then you got the steel under the roof, so that the water from the firefighters couldn't get to the structural steel that easily. And then finally, there was a lot of metallurgical testing that was done on steel samples to correlate our observations of the intumescent paint of the temperature against the actual temperatures that the steel would be exposed to, at least for past 400 degrees Celsius. So with the metallurgical testing, they were able to cross-check the temperatures against our assumptions of the intumescent paint, and they actually cross-checked very well. But secondly, they also checked for the ductility of the steel. We took a bunch of samples of structural steel around the building where they're not critical, and they found that the ductility and in fact the strength of the steel was not affected. So that was pretty good news.
Great, interesting.
Yeah.
Thank you very much again, Jeremy and Linus. That was fantastic. Thanks for those two examples, and thank you also for the questions and answers from everyone.